This video is an aid and introduction to fabric covering featuring the Polyfiber covering process. It does not replace the Polyfiber covering manual. Please read and consult the manual. This video is divided into 9 chapters.
Many different areas of expertise go into the building of an airplane. One of the most important is fabric covering. When home builders discuss fabric covering, one name stands out as a recognized leader, Ray Stitz. As one of EA's earliest members, I've come to know Ray very well. For more than 4 decades, Ray has helped lead the Homebuilt movement. He has designed more than 15 aircraft in addition to developing a fabric covering system that is universally acknowledged as the best there is. Perhaps the most important feature of Ray's system is its resistance to combustion, an area we'll cover in greater detail later. On behalf of the EAA Aviation Foundation, which is responsible for bringing this video to you, I'm very proud to introduce this guide to the Stitz fabric covering system. I encourage you to read the Polyfiber system manual in conjunction with this video for the best results possible. And now, here's Ray Stitz.
Hello, my name is Ray Stitz. I've been involved in aviation and fabric-covered aircraft since the late 30s. Now I want to talk to you about aircraft fabric. Fabric-covered aircraft account for approximately 30% of all general aviation aircraft in the United States in 1986. And that tabulation does not include thousands of gliders, gas and hot air balloons, unregistered light aircraft, and custom-built sport aircraft operating in the experimental category. Until the development of suitable man-made fibers in the late 50s, the short service life of natural fibers, cotton and linen, was a major expense in maintaining fabric-covered aircraft, especially when stored outside.
With the adaptation of unfinished polyester fabric, usually referred to as gray goods to cover aircraft, it is now theoretically possible for the covering to last longer than the metal or wood structure underneath it. This is possible because ultraviolet protective polyester does not deteriorate with age or fungus like natural fibers, dry rot like wood, or rust and corrode like steel or aluminum. However, many aircraft covered with polyester fabric are still being recovered in 3 to 7 years due to fabric deterioration, coating adhesion and cracking problems, and loose or excessively tight fabric. We hope this presentation will help prevent such mistakes by offering helpful information.
In 1962, during the course of designing and building my 15th aircraft, the folding wing Stitz Playmate, I decided also to develop a superior covering method using coatings formulated especially for polyester fabric on aircraft, rather than compromise and use unsuitable automotive and cellulose dope coatings.
The Polyfiber covering process utilizes the natural characteristics of unfinished polyester filaments to shrink and hold the correct tension when controlled heat is applied. Unfinished polyester fabric tends to shrink when heated. That's because after hot viscous polyester polymer is extruded through small orifices to form the filaments, they are again heated and stretched to about 5 times their original extruded length. This adjusts the filament size and improves its physical characteristics. It cools while stretching, which then locks in a memory. All other types of aircraft covering fabric, such as cotton, linen, and glass fiber cloth, each requires the application of cellulose dope coatings, either nitrate or butyrate dope, which shrinks as it dries and bonds to the fabric to produce a tight panel. Cellulose dope will shrink and develop tension on any type of woven material.
For the benefit of those who are not familiar with the very high strength and toning characteristics of dope coatings, I have a few test panels. This test panel is cotton canvas with 7 coats of butyrate dope. And this test panel is cheesecloth with 15 coats of butyrate dope. It's pulled so tight it's warped the heavy aluminum angle frame. And this panel is pantyhose, nylon pantyhose. Even though right across the center is strong enough to support my 190-pound weight. And this next text panel is plastic window screen with 7 coats of what is supposedly non-toning dope. With a dope covering system, the fabric acts only as a film former and carries no load until the dope film ages and cracks.
Once again, in dope covering systems, regardless of trade names, the dope finish creates the tension, not the fabric. As you'll see later, flexibility and durability may be a problem. Polyfiber fabric is custom woven from select polyester filaments to a specified thread count equal in warp and fill. When properly installed and a controlled temperature of 350 degrees Fahrenheit is applied, the tension developed will be between 1 3/4 and 2.5 pounds per inch, depending on the fabric style. It will never increase with age or heat from the sun and will not decrease in cold weather. Unlike metals, polyester fabric tends to expand at low temperatures. The only authorized heat source for accurate control of the temperature transferred to the fabric is a clothing iron, not a hot air gun. A handheld hot air gun cannot apply heat at a controlled, known temperature on a wide fabric area with the same consistency as an iron. The temperature at the center of the air blast from this 1200-watt air gun is 1,000 degrees Fahrenheit. The temperature transferred to any surface being heated will depend on the distance and the time. In about 4 seconds, a wad of newspaper will ignite, or a hole will melt through polyester fabric. In about 2 seconds, nitrate dope on polyester fabric will ignite. The iron should be rated at a minimum of 1,100 watts. Smaller irons do not have sufficient heat gain to offset a structural heat sink and hold the selected temperature throughout the fabric shrinking procedure. The iron thermostat should be capable of holding an accurate temperature setting within 10 degrees. Therefore, it is important that the iron be good quality. A current list of models we have tested and recommended is available through Polyfiber distributors. The iron is calibrated and the thermostat position marked to indicate 200, 225, 250, and 350 degrees while the iron is sitting on a half-inch thick stack of paper towels for insulation. A thermometer is placed between the paper towels and the iron in the center of the iron sole plate to indicate the temperature. The thermotransfer from the iron surface to the thermometer is more accurate through a white pigmented silicone heatsink compound commonly used on electronic components. It is available at electronic stores and through Polyfiber distributors. All silicone must be thoroughly cleaned from the iron surface before contact with the fabric. Otherwise, the coatings won't bond. A deep fry, candy, and jelly thermometer with the glass shell removed and the calibration checked in boiling water, 212 degrees at sea level, is a very economical thermometer source. A similar high-temperature glass thermometer is also available through Polyfiber distributors. During a covering job, there may be many non-load carrying areas that cannot be reached with a standard-sized clothing iron, and where exact fabric tension is not important as long as the wrinkles are removed. In that event, we recommend a small 165-watt heat-sealing iron, which is used for dozens of applications, including shrinking polyester film on model aircraft. It is available through local hobby shops and through Polyfiber distributors. It should be calibrated the same as the large iron and used only in areas not subject to flight loads, and to smooth the edges of trim tapes and patches, because these little irons are not capable of maintaining the selected temperature on a large heat sink. The 200-degree temperature is used to thermo-soften and level any coating ridges or drips to reduce sanding and to remove creases from fabric patches without shrinking. The 225-degree temperature is used to smooth and level any rough cement seam edges before tapes are applied, smooth the edges of all finishing tapes and patches, and heat-form fabric around corners. The 250-degree temperature is used for the initial shrinking of fabric panels and to smooth wrinkles from overlap cement seams before final heat shrinking and remove creases while lightly tauding the fabric over plywood surfaces. The 350-degree temperature setting is used for the final panel shrinking to develop the maximum tension. The highest temperature in combination with the type and size of the filaments, the thread count, and fabric slack when installed determines the tension. Polyester filaments become liquid again at about 486 degrees. At approximately 910 degrees, there will be sufficient outgassing to support combustion, and it will continue to burn. Polyfiber coating products are Polytack, a fast-drying, superior bonding fabric cement used to attach the fabric to the airframe as a substitute for machine or hand-sewn seams. Polybrush, as the name implies, with one exception, is applied with a brush as a fabric first coat and to install all finishing tapes and reinforcing patches. It is tinted with a red oxide pigment as an aid in uniform application and is also available untinted, so only the white fabric will show on the opposite side. Polyspray is an aluminum pigmented coating applied with a spray gun to block all UV radiation and is a sanding base to develop a smooth finish. Polytone is the standard finish and available in a wide range of standard and custom colors. A flexible two-part polyurethane enamel, aerothane, was developed especially for aircraft fabric and is recommended when a very durable, chemical, and weather-resistant high-gloss finish is wanted. Polyester finishing tapes, reinforcing tapes, sewing threads, and rib lacing cord completes the list of polyfiber materials. The polyfiber covering process has been approved by FAA under a supplemental type certificate to replace the original fabric covering on all aircraft which were mass-produced in the United States and most aircraft which were in limited production. There are no wing loading or airspeed limitations on any of our fabric styles. All covering materials are manufactured or processed under the authority of a Parts Manufacturer Approval, PMA, which is periodically renewed after an inspection to assure the quality of the products being manufactured and processed are the same as when the supplemental type certificate was first issued. Many of us who've been involved in aviation for many years remember gruesome accidents where friends were burned to death in a fast-spreading fire when they were trapped or could not get out fast enough after a minor accident in a cellulose dope and fabric-covered aircraft. Therefore, one of the important characteristics specified as a goal when developing the polyfiber coatings was that they would not support combustion and would self-extinguish when the fuel source was removed. We have already seen that bare polyester fabric will continue to burn. This is a sample of polyester fabric with just 2 coats of polybrush. The fabric will melt. However, when the fuel source is removed, the fire is extinguished. We frequently receive reports from people who were flying aircraft covered with polyfiber materials and survived an accident involving a fire, which did not spread. For the enlightenment of those who were not familiar with the fast-burning characteristics of cellulose coatings, we will test a few samples on different types of fabric. This first sample is clear nitrate dope on polyester, and it burns rapidly. Next is cotton fabric coated with nitrate dope through an aluminum pigmented nitrate dope finish, and it also burns rapidly and with a noticeable sparkle effect due to the aluminum pigments. Next is a sample of blue-tinted nitrate dope called DAC-proofer, and claimed by the manufacturer to give a complete fire-retardant system with 2 coats on polyester fabric. Don't bet your life on it. This sample burns just as fast and hot as untinted nitrate dope, Next is aluminum pigmented nitrate dope on polyester, which burns with a noticeable sparkle due to the aluminum pigments. The next specimen is clear butyrate dope on polyester. It has a burning rate a little less than the untinted nitrate dope. This sample is aluminum pigmented butyrate dope on polyester, which burns about the same as nitrate dope due to the aluminum pigments. Last, we have a sample of glass fiber completely finished with butyrate dope. The burn rate is about the same as butyrate on polyester, however, only the dope film burns, and the glass fiber is left intact with some of the aluminum pigments attached. All cellulose coatings are very flammable regardless of advertising claims, trade names, or color tints, and are safe as long as there is no ignition source, just like a tank of gasoline.
And now I'll review some fabric specifications and demonstrate some characteristics of polyester fabric.
While polyester is the most engineered man-made fabric in the world and most suitable material to cover an aircraft to date, there are two major handicaps as an aircraft fabric: high elongation when not properly installed, and a very smooth surface which resists good bonding. The qualifications for grade A cotton fabric used to cover civil aircraft is specified in Technical Service Order C-15, and these specifications have been used as a standard when qualifying other types of fabric to replace grade A cotton. Included among many specifications are a minimum breaking strength of 80 pounds per inch and a maximum elongation of 14% with a 70 pound per inch load in both warp and fill. Meeting the maximum elongation limits is only one feature that distinguishes Polyfiber custom woven fabric from dozens of look-alike styles that are woven for hundreds of commercial purposes, such as sailcloth and awning materials. All tests on fabric are made by a qualified testing laboratory and verified with a test report. The 14% allowable elongation with a 70-pound load is not adequate criteria for any fabric which will not be taughted with cellulose dope. When a specially designed polyester fabric does meet the elongation limits, it will be an equal replacement for dope-taughted fabric only when it is properly installed and heat-taughted.
To verify that statement, I'll demonstrate some of my standard evaluation tests.
The first demonstration with this test rig will be fabric tension at 25-degree heat increments starting at 225 degrees. This 2-inch wide strip of fabric is styled D103, and the iron contact area is exactly 50 inches long. The tape routes under a roller to pull directly on the dial scale. All slack is removed by adjusting the turnbuckle, and the scale still indicates no tension. At 225 degrees, the tension is 15 ounces. At 250 degrees, the tension increases to 1 pound 10 ounces. At 275 degrees, the tension is 3 pounds 4 ounces. At 300 degrees, the tension is 4 pounds. At 325 degrees, the tension is 4 pounds 5 ounces. At 350 degrees, the tension is 4 pounds 7 ounces, which is almost 2¼ pounds per inch width. At 375 degrees, the tension is starting to release and now reads only 4 pounds 6 ounces. At 400 degrees, the tension has dropped to 4 pounds 1 ounce. And at 425 degrees, as expected, the filaments have weakened as they start to melt, and the fabric has separated. As indicated by these tests, the maximum tension is developed at about 350 degrees, and if not heated at least to that temperature, loose fabric which balloons between the wing ribs under flight loads and expands and wrinkles in cold weather can be expected. While the drop-off in tension is rather flat when approaching 400 degrees, there is a narrow range between 400 degrees and the temperature the filaments will separate. The 350-degree target leaves a little safety margin for an erratic iron and inaccurate temperature calibration. Next, we will demonstrate the tension when the fabric is installed with a lot of slack. The 7 to 10% shrinking capability, depending on the fabric style, should not be misconstrued to mean the fabric should be installed with a lot of slack to be absorbed by heating. We will install another 2-inch wide strip of D103 fabric with 2 inches of slack, which calculates to 4% excess material to be absorbed in the 50-inch long heat shrink area. With the iron set at the initial 250 degrees heat shrinking temperature, tension comes up to 1.5 pounds. And the final temperature setting of 350 degrees, the tension is only 3.5 pounds. The previous test showed that at 350 degrees, the tension was 4 pounds 7 ounces when the shrinking was started with no slack. There may appear to be no difference in a finished panel when the shrinking is started with a lot of slack. However, we will give another demonstration to show the further polyester fabric shrinks, the lower the modules of elasticity or resistance to stretch under load, which allows the fabric to balloon between the ribs, the same as inadequate heating. To demonstrate the elongation, we will use 35 pounds, which is only 1/2 the 70-pound load specified in the TSO C15 elongation test. The first test with a 1-inch wide strip of D103 fabric will have no slack, and the iron is set at 350 degrees. We will now mark the strip to measure the elongation and attach the 35 pounds of sandbags to the edge of the strip, which passes over the roller. Then release the clamp. The elongation reads 1.5 inches or 3%. Next, we will install another 1-inch wide strip of D103 fabric with 2 inches of slack or 4%, and then repeat the heat tauting at 350 degrees and heat only the original 50-inch area as the fabric shrinks. After marking the elongation starting point, we will attach the sandbags and release the clamp. The elongation now reads 3.5 inches or 7%, over twice the elongation with no slack. These types of tests confirm that polyester fabric will be an equal replacement for dope-tauted grade A cotton only when it meets all the specifications in TSO C15, particularly the elongation limits in both warp and fill, and is installed with as little excess material as possible and heated to 350 degrees with a calibrated iron. This is an air shot of an aerobatic aircraft covered with polyester fabric. The fabric ballooning between the ribs is very noticeable, and the big loss in performance was discovered on the first flight. The entire aircraft was then covered again. Many pilots don't notice loose fabric or have little fabric experience and believe it is normal. The effect from fabric ballooning between the ribs is a change in the airfoil thickness and shape, which may change the center of pressure travel and safe CG range. Most noticeable when comparing to the original flight test data is a loss of airfoil efficiency, which increases the takeoff run and reduces the rate of climb, service ceiling, and speed, and may change the stall and flight characteristics such as spin recovery. A loss in performance is usually blamed on the engine or propeller. Loose fabric rippling in the prop wash area will eventually fatigue and crack any finish, and the cracks are always blamed on the coatings rather than the workmanship. In 1981, we obtained fabric samples from 5 major aircraft fabric suppliers advertised in aviation trade journals and sent them to a testing laboratory for evaluation. Not one passed the elongation test specified in TSO C15, and 3 ranged between 19 and 22%. Before installing any questionable fabric, a copy of a satisfactory test report from a qualified testing laboratory should be on hand to include with the aircraft records. The cost of a test is less than the cost of a complete recover. Any fabric which does not have a stamp indicating the source and the letters FAA, PMA can be considered questionable. And even then, the test report may not match the particular fabric style. Test reports on polyfiber fabric are available on request. When installing pre-sewn envelopes, particular attention should be given to an oversized, baggy misfit, which leaves a lot of material to be absorbed by shrinking. Envelopes are sometimes made large to slide over fittings and other protrusions. However, it takes only a few minutes to slit open a misfit envelope and use a Polytack cement seam on the structure to remove excess material from the envelope.
And now that you have all the background information, we'll proceed with some fabric covering, and Norm Dolphin will be helping me here.
Installing fabric may seem technical and complicated when viewing the completed aircraft. However, it is a very simple procedure performed one step at a time with a few basic rules and guidelines. Any intelligent person with a little skill who will take the time to read and follow the Polyfiber manual can turn out an award-winning project. There are no shortcuts to a top-quality durable covering, either in labor or material. Before installing fabric on an airframe, a thorough inspection should be made to assure the structure is ready for covering, because it could be many years before the fabric will be removed. And even then, it will not be removed due to deterioration of the fabric, because polyester will not deteriorate in any environment in which aircraft, including ag aircraft, are operated. Acid rain, fog or dew, or sulfuric acid spilled from a battery will not harm polyester fabric, as in the case of cotton, linen, and glass fiber. A good covering job begins with good preparation, not the last coat of finish. For example, metal leading edges installed in several sections will slide at the overlap joint due to wing bending loads and thermo expansion and contraction just sitting on the ground, which causes wrinkles in the fabric at the overlap joint unless the leading edge sections are fastened together with rivets or screws to prevent sliding. Carelessly installed metal trailing edges will move forward a fraction of an inch under fabric tension and form small fabric wrinkles over the ribs, unless the trailing edge is securely anchored or fitted tight against the ribs to prevent movement. Chapter 4 of the Polyfiber Manual will address this further. A misfit leading edge fairing will also move and cause wrinkles over the ribs. Each step and all the options in preparing an old or a new airframe for covering, such as compatibility of old and new wood varnishes and metal primers, corrosion protection, applying anti-chafe tape on sharp corners to prevent fabric damage, and securing control cables and push rods before rib lacing is detailed in the Polyfiber Manual under the caption, Step 1, Preparation. Briefly, epoxy varnish is used on new wood, and to recoat any old varnish, an epoxy primer is used over bare metal, where needed, and to recoat any old primer. Polyfiber epoxy varnish and primer were developed to meet the special requirements of aircraft and will not lift any old coatings or be affected by any coating solvents. A layer of polyester flannel or non-woven padding may be used to cushion and smooth the dents in old aluminum leading edges. Padding is used only on convex surfaces, never on flat or concave surfaces where the fabric must bond to the surface to prevent ballooning. The padding may be attached only around the edges using polytack to prevent slipping while the fabric is being installed. Part of the preparation on this wing includes pre-coating the leading edge with 2 coats of polybrush, which has been reduced with equal parts of polyfiber reducer to provide a smooth flow out on the surface. The purpose of the pre-coat is to provide a good bond of the fabric to the leading edge and eliminate pinholes which are caused by escaping solvent vapors being trapped in voids in the fabric weave. Pinholes are a common problem with any type of coating on multi-fiber woven material. The recommended method to support wings this size when covering only one aircraft is to position them on sawhorses. Wood strips on the sawhorses, padded with scrap carpet to spread the load over 2 or more ribs, should be used to avoid rib damage. It is important that wings and all other components be properly supported during covering and finishing to prevent slipping or falling and damage. We are going to cover this Piper J3 Cub wing with our very smooth 1.7 ounce per yard, 90-pound strength HS90X fabric spanwise and use a polytack cement seam at the leading and trailing edges. In this case, the leading edge is acceptable and does not require a polyester padding under the fabric. If we were going to use polyester padding on the wing leading edge as demonstrated here, we would sew 2 pieces of fabric together with a seam down the leading edge, or sew multiple sections with seams running cordwise to form a blanket, and use the overlapped cement seam at the trailing edge. The first section of fabric is installed on the wing bottom side with the wing position level, listed as Step 2 in the manual. The fabric is spread over the wing and cut to length with a minimum of 1-inch overhang at each end. Use spring clamps to secure the fabric spanwise and cordwise. Position the fabric to extend a minimum of 2 inches past the wing leading edge center line. The top fabric could also be installed first using the same 2-inch positioning. There's no exact sequence to cementing fabric on a wing. However, we prefer to start at the wing butt and apply the polytack cement on a strip approximately 1 inch wide and 12 inches to 24-inch long increments on the surface of the leading edge. Apply sufficient tension to remove wrinkles from the fabric while rubbing the fabric surface firmly with the back of your hand or fingertips or the brush to cause the wet polytack coat to be forced up through the fabric weave. Do not apply additional polytack on top of the fabric surface because a sealing coat will delay the solvents wicking from the filaments and escape as vapors. The bond is between the underside of the fabric and the structure on which the fabric is positioned. A wet coat of polytack on top of the fabric will not add to the bonding strength, only delay drying. Pre-coating the surface with polytack and then using a solvent such as MEK to wet the fabric will bond only the small surface of each thread in contact with the dried polytack film. The strongest bond is made when polytack is forced up through the filaments. Anyone who is allergic to solvents or coatings should wear rubber gloves when using polytack, the same as other coatings, and the work area should be well ventilated. There are several hand creams available that are very effective in protecting the skin. The polyfiber covering process allows a wide latitude of fabric attaching methods not permissible with any other FAA-approved covering process, due primarily to the development of the proprietary formula, Polytack cement. Polytack avoids the necessity to machine sew or hand sew seams except for large components or wide chord wings when the available fabric width does not allow cementing the fabric directly to the structure around the parameters. A 1-inch overlap fabric-to-fabric polytack cement seam is stronger in shear loading than our strongest fabric, and in tension tests, the fabric always fails first. In peel tests reported in the manual, polytack develops over twice the bond as any nitrocellulose fabric cement. The polytack cement seam approval allows a 2-inch overlap at the wing leading edge and 1-inch overlap at all other areas of the airframe, each covered with a minimum 2-inch finishing tape regardless of the aircraft red line. All cement seams are made over a structure, not in open panel areas. After the full length of the leading edge is cemented, pull the fabric towards the trailing edge and secure with spring clamps. Rough trim along the trailing edge to overhang 1-inch minimum. The aileron recess is rough trimmed to allow the fabric to fold down the backside a minimum of 1 inch. Inside corners are cut 45 degrees to allow the fabric to fold down at the sides. Industrial-grade razor blades are very handy for trimming and fitting the fabric. Starting at the trailing edge, the fabric is cemented initially only to those trailing edge surfaces which are aligned with the fabric as it is pulled from the leading edge to remove all wrinkles. Protrusions such as wing strut fittings or any component which will hold the fabric from its final position more than 2 inches should be accommodated by cutting the fabric to fit around the protrusion during the initial fitting. 2 or 3 inches of the fabric around the holes should then be coated and sealed with 1 coat of poly brush before heat shrinking the fabric to avoid distorting the fabric weave. Small protrusions can be accommodated by cutting the fabric after heat shrinking and the first coat of poly brush, then heat shrink the wrinkles developed by the tension release. Next, the fabric is cemented to the butt rib. Then the fabric at the wingtip bow is cemented into place, starting at the trailing edge and working towards the leading edge to remove wrinkles. After the fabric is cemented around the complete wing perimeter, an iron at 225 degrees is used to form and shape the fabric around all sharp corners. After heat forming around all sharp corners, reverse the wing position to topside up. Any excess fabric at the butt end is trimmed, leaving approximately 1/2 inch to be cemented to the inboard side of the butt rib. The trailing edge fabric is trimmed to allow a wraparound to the forward edge and cemented in place. Trim around the aileron hinges and cement the fabric a minimum 1 inch up the backside of the aileron recess fairing. The fabric around the wingtip bow is trimmed to wrap past the center with 1 inch minimum contact area and cemented in place. After the cement is dried about 15 minutes, an iron set at 250 degrees is used to smooth any wrinkles or fabric folds around the perimeter, and especially along the leading edge before the top fabric section is installed. Polytack cement will thermo-soften and allow the fabric to shrink and remove all wrinkles and not ignite with a hot iron, like nitrocellulose cement and dope. The top section of fabric is rolled out and cut to length, the same as the bottom section. The alignment along the leading edge is made first, overlapping the bottom fabric 2 inches minimum, which places the top fabric edge on the center of the leading edge. The 2 inches or wider finishing tape to be installed later will be centered over the fabric edge, and will also provide an abrasion buffer on the leading edge. Cement around the complete perimeter the same as the bottom section of fabric, starting on the leading edge at the butt end. The compound curvature on some wingtips causes excess fabric to develop as it is smoothed and cemented in place. Small excess fabric areas may be absorbed by heat shrinking with an iron at 250 degrees using a cardboard support under the fabric. The final tension of the total panel will be about the same regardless of the spot pre-shrinking. The same technique is used to absorb small areas of excess fabric around compound contours throughout the covering project. After the fabric is attached, use an iron at 225 degrees to heat form the fabric around the corners and contours. The wing is again reversed, topside down, and the edge is trimmed at the trailing edge and wingtip to overlap the lower fabric a minimum 1 inch. Excess overlap should be avoided to assure the fabric edge will be located to use 1 2-inch or wider finishing tape with a minimum 1 inch of tape on each side of the fabric edge to cover the seam, and also serve as the wear and abrasion tape normally installed on all corners and wear points. Sometimes a 3-inch or 4-inch tape is required. The fabric is trimmed and cemented to the concave surface of the aileron fairing with Polytack fabric cement to overlap the lower fabric 1 inch minimum. All bubbles and wrinkles are worked out as the fabric is smoothed with no tension. The wing butt is closed by cementing pieces of fabric cut to fit flat on the butt end with 1 inch minimum overlap on the top and bottom fabric. Excess fabric developed when folding 90 degrees over a curved surface such as the top of the butt rib should be absorbed with heat before cementing the fabric in place instead of slitting and overlapping, which looks amateurish and builds lumps on an otherwise smooth surface. After all fabric edges have been trimmed and cemented down, use the iron at 250 degrees to smooth all wrinkles in the cement seams and lay down any edges. When the last cement seam has dried about 15 minutes, the wing is ready for fabric shrinking. However, we are now going to put some fabric on the fuselage. It is not necessary to remove the engine and landing gear so the fuselage can be inverted and turned on its side during the fabric covering procedure. However, rotating the fuselage is very convenient, reduces the fabric work time, and improves the workmanship. A rotating jig supporting the front and aft end is preferred when working alone. An alternate is to bolt 2 wood 2x4s on the engine mount or firewall as legs to support the fuselage while topside up and inverted. 2 2x4s are mounted horizontally as legs for support when positioned on either side. A padded low sawhorse is used to support the aft end of the fuselage in 3 positions, and a section of scrap carpet on the floor may be used to protect the vertical stabilizer tip while inverted. There are many methods fabric may be installed on a fuselage using the Polyfiber covering system. A fuselage designed with a removable vertical stabilizer covered separately, which permits cementing the fabric to the 4 longerons and structure at the front and aft ends, may be covered by attaching the fabric in 4 sections, or any combination of areas depending on the available fabric width. This cub fuselage will be covered with 3 pieces of fabric. The first section will be glued on the left upper longeron to the right lower longeron. The second section will cover from the right lower longeron to the right upper longeron. The third and final piece will run from the right upper longeron over the top of the fuselage and to the left upper longeron. All attachments where the fabric terminates and the tension is in one direction, such as the forward fuselage area, should be pre-coated with 1 coat of Polytack cement on all sides to assure a good bond. We're going to install the fabric in sections with cement seams everywhere except 2 machine-sewn seams to cover the vertical stabilizer. To conserve fabric, we will cover the large areas first and use the trimmings to cover smaller components. The fabric type is HS90X and the width is 70 inches. The first section will be the left side with the fabric cemented to the upper longeron and extending around the bottom of the fuselage to the right lower longeron. The fabric is held in place with spring clamps. Then, starting at the forward end, attach the fabric with Polytack cement, the same as demonstrated on the wing. When the full length of the longeron is completed, pull the fabric snug. rough trim 1 inch past the longeron, and cement to the right lower longeron starting at the forward end. Don't be too generous in fitting and trimming the left side because the remnant must be large enough to fit the other side. Due to the bend in the lower longeron at the forward end, we will have to slit the fabric and remove the excess with an overlap cement seam. After the fabric attachment is completed to the tail post, we can cement the forward end with the fabric trimmed long enough to wrap 270 degrees around the C-section. Next, roll the fuselage on its left side and trim off the excess fabric and roll the edge around the tubing and cement it into place. After the cement is dried about 10 minutes, we can use the iron at 250 degrees to remove any wrinkles which may show when the next piece of fabric is installed. Next, take the fabric trim from the left side and reverse the end and cement to the right lower and top longeron, the same as the left side, using the same procedure. Next, we will turn the fuselage upright and cement all the ends of the fabric on both upper longerons. After the cement on the upper longerons has dried 10 to 15 minutes, the iron again is used at 250 degrees to remove all wrinkles which may show through the second piece of fabric. The top of the fuselage is covered by first centering and clamping the fabric on the fuselage aft of the skylight, then centering and slitting the aft end to fit on each side of the vertical stabilizer and secure with clamps. 2 pieces of trimmings are fitted on each side of the vertical stabilizer and attached to the fuselage section with T-head pins. After checking again for fit, we can rough trim about 1 inch below the longerons, then the fabric is removed to machine sew the 2 seams. The modified folded fell seam illustrated in Figure 2, Detail E, is usually used on 100% polyester fabric because it is very smooth and slippery and difficult to handle in comparison to cotton or textile blends. The plain overlap seam illustrated in Detail A and B is also used quite often. The machine sewing thread has a strength of 10 pounds, and the machine stitches will be no less than 10 per inch. Very few new all-plastic models of domestic sewing machines will sew with the heavier thread, and older models or commercial machines are usually used. When a sewing machine is not available, a combination of cement seam and hand-sewn seams, as illustrated in Figure 3, may be used to install fabric on a fuselage with an attached vertical stabilizer. Typical locations for hand-sewn seams is illustrated in Figure 4. After the machine sewing is completed, the top section is positioned on the fuselage and held in place with spring clamps. Start cementing at the top of the fuselage aft of the skylight with the overhang long enough to wrap 270 degrees around the C-section. Special attention should be given to duplicating the original manufacturer's technique of attaching the fabric around a skylight on a high-wing cabin aircraft. Next, trim and fit the overlap seam on the front and top of the vertical stabilizer. Then, trim and fit around the windows. Next, start working aft along the longerons to the tail post, then down the tail post. There is very little scrap fabric when covering the fuselage with the procedure demonstrated. After close inspection to assure all fabric attachment is completed around the parameter, the fuselage is ready for the heat tauging procedure, and we will now put fabric on some control surfaces and a landing gear leg. Due to the configuration of this rudder, it is covered with 2 pieces of fabric. Lay the rudder on a piece of fabric and mark around the outline with a ballpoint pen. Then trim about 1 inch outside the line. With the fabric clamped to avoid slipping, start the cement seam along the hinge tube, then out the counterbalanced rib, then around the outside edge. After the ends are heat formed to fit the contour and cemented in place, and any wrinkles smoothed with the iron as demonstrated earlier, the other half is fitted and attached in the same manner to provide a minimum 1 inch fabric to fabric contact. Control surfaces with one straight edge, such as this horizontal stabilizer, may be covered with one piece wrapped around the hinge tube and a cement seam used around the leading edge and inboard sides, or covered with two pieces of fabric. The same option applies to the landing gear legs. We can use two small scrap fabric pieces or one large piece. The aileron may also be covered with one piece with a cement seam at the trailing edge and ends, or two pieces with cement seams on all sides. An elevator with a curved trailing edge is covered with one piece wrapped around the hinge tube, or two pieces the same as the horizontal stabilizer. All components we have covered are now ready for Step 3, heat taughting, and we will start on the wing. As a test to check whether the shrinking is uniform, we will put a mark with a ballpoint pen on the top of several ribs. And when the taughting operation is completed, we will see if the marks are still located on the top of the ribs. Ballpoint ink doesn't bleed through a finished coat. The shrinking procedure is accomplished by moving the iron set at 250 degrees temperature in light contact with the fabric surface at 4 to 7 inches per second. A faster speed will not transfer sufficient heat, and a slower speed would be unnecessarily time-consuming. Do not attempt to remove all wrinkles from one area before going to the next. The iron should be passed briefly across each panel area and wrinkles removed uniformly. Several passes at 250 degrees are recommended, working briefly in each area. After all the wrinkles are removed on one side of the wing, it is turned over and the other side taughed at 250 degrees in the same manner. After all areas on both sides have been heat taughed and wrinkles removed at 250 degrees, the temperature is increased to 350 degrees, and again, moved in contact over all areas at 4 to 7 inches per second. The two-step shrinking technique is intended to avoid distortion of the fabric weave pattern and any seams when all the shrinking takes place in a few areas. The appearance of smoke from the fabric at the 350-degree iron setting indicates moisture on the filament surface as being removed as steam and is normal and not cause for alarm. Fabric-forming structures such as a leading edge act as a heat sink and will require the lower end of the speed rate. The iron is first moved briefly from one area to the next rather than completing one area before moving on. After the first brief pass, the iron is moved carefully to contact all the fabric surface. The 350-degree iron temperature setting cannot damage the fabric regardless of the number of passes over one particular spot, or left sitting with no movement indefinitely. Rather than risk missing a few spots, it is best to make several passes as an assurance all the fabric surface has been in contact with the iron at least once. It should be clarified that excess fabric tension, which warps and damages an airframe, can be caused only by many coats of cellulose dope in combination with heat-taughed fabric, and never by heat-taughding alone. Any airframe that was originally covered with cotton or linen and cellulose dope will not be damaged by the tension developed with polyfiber fabric. With the fabric taughding complete, we can check to see if the marks over the ribs have been pulled off position. The marks are still centered on the ribs. After the fuselage and control surfaces have been heat-taughed, it is time for the first coat of polybrush, detailed in the manual as step number 4. However, we will postpone step number 4 and put some fabric on a plywood wing. Aircraft plywood surfaces are usually covered with fabric for weather protection because years of service experience have proven the fabric provides the most suitable means of protecting the plywood from abrasion damage and preventing the plywood grain from cracking and opening in the weather. The choice of fabric styles for covering over plywood will depend on the aircraft design. Fabric approved to carry air loads must be used on semi-plywood covered components. If a component has only a few open sections, a combination of D104 over the plywood and a stronger fabric over the open areas could be used. In that event, a 1-inch fabric overlap on the plywood covered with a 2-inch tape is recommended. Plywood components with no open fabric panels, such as this Bolanka wing, may be covered with lighter D104 style polyester fabric, authorized for use only over plywood because the fabric carries no air loads. Fabric may be installed on plywood in strips or sections in any direction in relation to the slipstream. All plywood surfaces should be checked and any small depressions filled and smoothed. Polyfiber lightweight fast-drying composite surface filler, Feather Coat, mixed with micro balloons to make a slurry, was used to fill and smooth many small gouges on this wing. The preparation of plywood surface for covering is detailed in the manual under step number 1, preparation, and includes epoxy varnish over any old varnish or new wood, then 2 brush coats of polybrush over all the plywood surfaces which will be covered with fabric to provide a good bond for the fabric to eliminate pinholes and assure it doesn't balloon and lift off the plywood surface due to aerodynamic loads. Each fabric section is positioned and cemented only around the perimeter. A fabric splice over plywood is not critical and may be overlapped an inch with no finishing tape or trimmed with a razor blade and straight edge to butt the ends and later covered with a 1-inch tape. To remove wrinkles in a polytack cement seam over plywood, the temperature is increased to between 250 and 350 degrees to offset the heat sink. The heat shrinking procedure for polyester fabric over plywood is different than open panel areas. The iron is used at 250 degrees to remove fold creases and wrinkles which will show through the finish coat. Full fabric tension at 350 degrees is not used because it will bridge or pull fabric out of any shallow low areas of old warped plywood components. The plywood heat sink under the fabric requires slower movement of the iron to heat the fabric. After fold creases and wrinkles are removed, the surface is ready for the first coat of polybrush. But first, we will clean the surface. During production and handling, polyester fabric attracts and holds thousands of lint, dust, and dirt particles ever present in the air and on workbenches, which may show as tiny bumps with the first coat of polybrush. A vacuum cleaner, air blast, or tack rag wiped lightly across the surface is recommended just before the polybrush application. Polybrush, thinned with equal parts of polyfiber reducer, is brushed through the fabric to soften the underlying precoats of polybrush, to embed and saturate the fabric to exclude all air. Work from one side across the surface to remove all bubbles. Where fabric tends to raise from lower areas of a plywood surface, a second pass with a brush approximately 30 seconds after first wetting the pre-coated surface will develop sufficient adhesion to hold the fabric down in the low areas if the depression is not too deep. If a plywood surface has a deep warp and the fabric will not stay down, the most practical fix at that late state is to coat all the surrounding area to stabilize the fabric. Then, carefully cut the fabric across the center of the void and cover the slit with a finishing tape. Fabric over small protrusions can be cut after the first coat of polybrush is dried to stabilize the fabric, and all openings are also cut and trimmed after the first coat. We will now go back to the cub wing, fuselage, and control surface and apply the first coat of polybrush after cleaning dust and lint off the fabric. Polybrush penetrates and wets the fabric so it becomes translucent with less run-through when applied with a brush, if reduced about 3 parts to 1 part reducer. Excessive first coat application which drips off the backside onto the opposite fabric or runs down a vertical surface should be avoided. However, other than cosmetic, there is no harm done. Do not add polytack to polybrush to increase the adhesion, because polybrush already has all the adhesion needed, and the fast evaporating solvents in polytack accelerates the drying time of polybrush. Apply the polybrush in wet uniform strokes. Do not continue brushing after polybrush starts to dry, because it will rope or drag on the brush and may show as a rough surface through the finish coat. First coat brush patterns other than roping never show, because polybrush penetrates and levels with the surface of the fabric. If the appearance of the coating buildup is not satisfactory at any stage during the coating procedure through to the finish coat, use a new lint-free cotton cloth soaked with polyfiber reducer to remove the coatings to the bare fabric and start again. Don't use old laundry or shop towels which will contaminate the surface. Those areas of the fabric passing over fairings, such as leading edge, are coated with the polybrush reduced with equal parts of polyfiber reducer, the same as the plywood wing. Starting at one side, brush sufficient polybrush through to soften the underlying coating and thoroughly saturate the fabric weave to fill all voids. The first coat of polybrush may also be applied with a spray gun, but over fabric panel areas only, not over plywood or the leading edge. Instructions for spray gun application are detailed in the manual under Step 4. The first coat, whether by brush or spray gun, must close the fabric porosity to avoid pinholes. After the poly brush is dried 15 or 20 minutes, it is time for step number 5, rib lacing. Various methods are used other than lacing cord to attach fabric to an airframe. Most common on post-World War II aircraft are screws, blind rivets, and wire clips or barbs. Attaching fabric by any method other than specified by the original manufacturer requires an approval by FAA. Fastening the fabric to ribs with hardware such as screws and rivets, duplicating the manufacturer's method, is quite simple. However, rib lacing is the most difficult. Therefore, we have chosen this cub wing, which requires rib lacing, to demonstrate the procedure. Adhesive-coated polyester reinforcing tape, the same width as the rib cap, is positioned over the ribs to extend a minimum 1 inch past the last rib lace at the leading and trailing edge. The shear strength of our custom-woven adhesive-coated polyester reinforcing tape exceeds the required minimum 40 pounds breaking strength of rib lacing cord by a wide margin. We do not use glass fiber strapping tape for reinforcing tape because, like all glass fiber products, it is strong in tension but has very low shear and chafe resistance. Low-wing loading slow aircraft may fly for years with seemingly satisfactory results with weak rib lacing. However, when inadvertently caught in turbulent air conditions, gust loads can break weak rib lacing in a rapid domino effect and let the fabric peel from the wing in seconds. There have already been several fatal accidents caused by glass filament strapping tape shearing through and allowing the fabric to balloon and rip off the wing. The manual warns against dangers of gluing the fabric to the ribs as a substitute for a proven mechanical attachment. When the original rib lace spacing is not known, the spacing given in Figure 10 will be used. The rib lacing chart shows spacing for this slow J3 cub should be 3.5 inches outside the prop wash area and 2.5 inches inside the prop wash area. This is the maximum spacing for any aircraft regardless of the red line. The prop wash area is considered to be the propeller diameter plus 1 rib. With a 72-inch prop and the spar IB fitting being near the aircraft centerline, the first 2 inboard ribs will be laced 2.5-inch spacing and can be laid out using a measuring tape. The first lace will be spaced from the leading edge fairing no more than 1/2 the required spacing shown in Figure 10. For example, if the spacing will be 2.5 inches, the first lace will be 1.25 inches from the leading edge. After marking the lace spacing on the first rib outboard of the prop wash area and the last full tip rib, a chalk line is snapped across all the ribs to align the spacing. The smaller tip rib is marked by extending the chalk lines from the last full rib. Then, holes are punched adjacent to the ribs with a needle. Alignment of all rib lacing is not required but recommended for aesthetic purposes, and it also indicates a little pride in workmanship, a rare commodity. This chart shows the 2 different rib stitch spacings used on this cub wing. The inboard prop wash ribs are shown in red. The outboard key ribs are green. Each of these key ribs, as we call them, has 2 keyholes. As you will see later, these keyholes are used as a guide for the elastic band. Next, we push a needle through the wing with the needle parallel with the spar face at the trailing edge and leading edge in the prop wash area, in the same key ribs outboard of the prop wash area to mark the locations on the bottom side of the wing. To ensure the lace spacing on the flat bottom of the wing will be reduced proportionately to match the locations on the top of this high camber airfoil, with the lacing cord parallel to the spar face, we will develop proportional spacing by stretching an elastic band, about 20% across the top of the wing, and mark the lace locations on the elastic. One side of the elastic is used for prop wash area, the other the outboard spacing. The wing is then turned over and the marks on the elastic is matched to the leading edge and aft locations, which were marked by the needle holes at the last full tip rib and the first rib outboard of the prop wash area. The lace locations are marked, then a chalk line is used to mark all the ribs in between, the same as the top surface. The two prop wash ribs are marked from the elastic and the lacing holes are punched adjacent to the rib with a needle, and then the chalk lines are wiped off with a clean rag. Wings with a rib cord up to approximately 4 feet can usually be rib laced with one length of cord without loss of time untangling the excess length or fraying the cord and wearing off the wax coating by repeatedly pulling through the fabric. Wider cord wings with thick sections are best rib laced with several cord lengths 6 to 8 feet. At the end of the cord, the knot is tied off with a half hitch, then start with a new cord or a new length can be tied on the end using the splice knot illustrated in Figure 11. The length of cord required to lace a complete rib will depend on the wing rib thickness, lace spacing, and rib length and can best be determined after experience with a few ribs. We will plan on using 2 lengths on these ribs. Polyfiber rib lacing cord, either flat or round cross-section, may be used, and both are impregnated with a microcrystalline fungicidal wax. A floodlight under the wing, silhouetting through, aids in avoiding control cables and tubes and helps find the holes when pushing the needle through the wing. We're going to use the Polyfiber hidden rib lacing knot, which positions the knot inside instead of leaving bumps on the outside. It is the same modified seine knot illustrated in Advisory Circular 43.13-1A, which can also be used, but the tying procedure is a little different. To help the camera pick up the details of the knot tying procedure, we've coated a short section of rib lacing cord with lamp black, which bonds to the wax and will not bleed. The rib lacing procedure is started by passing the needle through the pre-punched holes at one end of a rib, through the bottom, and back up the other side. Then, tie a square knot, as illustrated in Figure number 13, Step 1. A simple way to tie the starting square knot is to fold the longer cord double and loop over. Then, pass the short end through the loop. We will demonstrate again, then lay the knot out to show that it is a square knot. After the square knot is pulled tight, each end of the cord is secured with a half hitch, as illustrated in Figure 13, Step number 2.
Drive it on down. Okay, how's that? Show that? Now, we can slide this needle, this here.
Before pulling the knot tight, the end of the short cord may be positioned under the knot, and after the square knot is pulled tight, the end is passed through the loop to form a half hitch.
Push through. That's the first half hitch. Take the other. Go under. Second half hitch. We're going to cut this short now.
Let's repeat the procedure with the camera. After both ends of the cord are secured from slipping with a half hitch, the needle is routed back through the hole at the right-hand side of the rib and out the next rib lace position, as illustrated in Figure 13, step number 3. All the cord is pulled through to the new rib lace position. The needle routed back through the same hole to the opposite side of the wing, as illustrated in Figure 13, step number 4. The cord is pulled through to the opposite side of the wing, leaving approximately a 3-inch loop on the top side, and the needle is passed up through the loop, as illustrated in Figure 13, step number 5, with cord section A, which routes from the previous knot passing forward of the needle.
Now, we want to get the one that comes from here, but in front. Can you get that now? How's it looking?
The needle and all the cord is then pulled through to the top side, and the needle hook used to pull cord section A under cord section B, as illustrated in Figure 13, step number 6, while holding cord section D perpendicular to the surface.
On top of that, and back under.
The length of the needle through the loop should be about the same as the loop length. The needle tip is then passed over cord section A and under cord section B, as illustrated in Figure 13, step 7. Then, over cord section D, as illustrated in Figure 13, step 8, and all the cord is then pulled through the knot while holding cord section D perpendicular to the fabric surface to avoid cord entanglement. Next, remove all slack from the loop passing around the rib by pulling firm on cord section D perpendicular to the fabric surface, as illustrated in Figure 13, step 9. After the loop around the rib is pulled tight, with all the slack removed by pulling firm on cord section D, the thumb is positioned over the knot, and the knot is secured by pulling on cord section E, as illustrated in Figure 13, step 10.
And take this section here and drive it home. Done. Pick up the next one, go under. Disappears.
Let's repeat the procedure with the camera.
Pushes up. Okay. Right. Now this is the one that comes from back here. And we'll keep about that much for loop. Hang on to this one. Go under, and we catch that one. Get another there. Got that so far. We want the same distance from here to here. So we can roll over, go under there. Got that?
I can see that now.
Now, over, that,
That's it.
now. Now, get my head out of the way.
So pull it through slow, so you watch the needle. They follow the bare pieces, so you get that little one gets out of the way. How they see it?
Now repeat this one here. Only section D. Keep tightening up. And heading away.
Now we see the
Move in. Don't let go. Now it's snug. Now we transfer. Take this here. Put the thumb right here. Take this here. That's the needle end.
can't see that end of it. So watch it now.
Done.
After all rib lacing is completed on the rib, then tie-off is made with a half hitch as illustrated in Figure 13, step number 11. The needle is then routed back through the wing and the knot is pulled through the hole, then the cord is cut. During the rib lacing procedure, any internal stationary obstruction may be circumvented by routing the needle forward or aft adjacent to the rib. Pull the needle through, then return through the same hole and exit at the desired location. When a control tube or cable will chafe the rib cord, the fabric may be laced around the rib cap a distance of a single rib lace spacing on both top and bottom rib caps. A tie around a rib cap is made with a curved needle, usually 6-inch size. The needle is pushed through on one side of the rib cap, as illustrated in Figure 14, step number 1, and out through the fabric at the opposite side, adjacent to the rib. Then, routed back through the same hole to a position opposite the original entry hole, and all the cord pulled through.
Over here.
A square knot is tied and pulled tight. The end secured with a half hitch and then the knot pulled inside and the ends cut off. The same procedure is used to duplicate the original manufacturer's methods of attaching fabric to rib caps above or below a fuel tank or other large structures where a needle cannot pass straight through the wing.
Okay. Take this one. Feed it back under here. Leave it lay. Now take this in and push it through. See it?
Nope.
Over. Both of them and go tight that way. Can I have the scissors down there? Damn it. Got this now?
Mm-hmm.
Take this and go anywhere.
After all rib lacing is completed, a check is made to assure the rib lacing does not interfere with any control cables, tubes, or rods inside the wing. When the original lace spacing on tail surfaces is not known, the recommended spacing is twice the spacing in the prop wash area on the wings. For example, if the spacing in the prop wash area is 2.5 inches, all tail lace spacing would be 5 inches. The reinforcing tape can be continuous or cut in 2-inch lengths centering on the individual rib lace. A single lace tie is started the same as the continuous rib lace by passing the needle around the rib and tying a square knot as illustrated in Figure 12.
Now again, we take the thing again here.
Then tie a half hitch at each side of the square knot and cut the loose cord end short and pass the needle back through the fabric.
Like that. It flips over and becomes like that again.
Got it.
slip this under here. Hopefully. Then take the end through here, back again.
Good.
Cut the first half. The needle. Again.
Pull on the cord to cause the loop to rotate and pull the knot through the hole. Then
Maybe
cut
turn
the
it over.
cord.
Good.
Turn it over. Good. Done.
Okay, good.
And now we will talk about false rib lacing. On aircraft originally certificated in the standard category, the wing rib spacing and other fabric forming structures are determined by the aircraft wing loading, and the rib lace spacing is determined by the aircraft red line. Many experimental aircraft with high horsepower engines installed and standard category aircraft modified with larger engines and increased wing loading do not have adequate structural spacing to prevent excessive fabric drumming on the wings, tail surfaces, and landing gear legs in the prop wash area, which causes coating fatigue cracks at structure edges. Sonic shock waves from large engine exhaust blasting directly on fabric-covered landing gear legs also causes coating fatigue cracks regardless of the type of fabric and coating. These design deficiencies don't appear until 200 or 300 hours flying time, and the fabric covering materials are always blamed for the problem. A practical method to change the natural frequency of fabric panels, such as landing gear legs and horizontal stabilizer, and reduce the drumming, is to install false rib lacing in the center of the panel areas. Depending on panel size, one or more single rib lacings may be installed to pull the two fabric surfaces slightly together. The needle is pushed through to mark the location on the opposite side, and a 1-inch length of reinforcing tape is installed. Then, the needle is passed back through the two surfaces and tied with a square knot and finished the same as the single lace demonstrated earlier.
So the same kind of a knot now. Same deal, we flip it over, so it is a square knot. Flip it down. Only tight enough to hold it together. Slip this in here. Just enough to hold the tension together. And go back through here. Same as before. And there. And here. Get my thumb out of the way. See what's coming through there?
Mm-hmm.
And cut that again. This is just enough pull to hold it tight. We'll go down through the same hole again.
Okay.
Got it?
Yep.
Now, let me show you something here on camera. This enough to get that?
The next procedure is to install inspection access hole reinforcing rings as detailed in step number 6. 3 9/16" inside diameter CAV plastic inspection access rings have become popular and bond satisfactorily with Polytac fabric cement. Any metal inspection access reinforcements of a particular shape, special design, or size installed by the original manufacturer should be reinstalled with Polytac after cleaning and epoxy priming. It is preferred all inspection rings be installed before any finishing tapes and reinforcing patches. Inspection access is provided adjacent or over every control bell crank, drag wire junction, cable guide or pulley, wing fitting, or any other component throughout the aircraft which will need to be inspected or serviced through the fabric covering annually. They are installed only on the side and bottoms of the fuselage and bottom of the wings, except where installed on the wing top surface by the original manufacturer. Sometimes, tail surfaces will have inspection holes. Cutting the holes may be delayed until needed. However, all inspection covers should be finished in matching colors with any trim lines and stored. Spraying matching colors a year later is expensive and time-consuming. Tapes or patches over aluminum access reinforcements are optional but recommended in the prop wash areas on the wings and forward fuselage bottom, which are subjected to continuous vibration from the prop blast. Fabric patches over plastic rings is also recommended because plastic is not a stable material. It becomes brittle at low temperatures and fatigues and cracks from prop blast vibration, and rings are often cracked during removal and installation of spring clip-held covers. Minimum 7-inch diameter patches cut from scrap fabric should be installed with polybrush. Any creases and small wrinkles in the patches can be removed with the iron set at 225 degrees after the first coat of polybrush is dried. Fabric to be used for patches may also be mounted tight on a rectangular wood frame and the iron used with the temperature set at 250 degrees to remove creases. Then, one coat of polybrush applied. After drying, the smooth, crease-free material is cut for patches. After the inspection rings are installed, the next procedure will be to install the finishing tapes and reinforcing patches as detailed in step number 7. Use only polyester finishing tape, not cotton, because cotton will deteriorate regardless of protection and storage conditions and will have to be replaced to protect the rib stitches and sewn seams. Pinked edge tape is preferred over straight edge tape because the pinked edge provides 41% more edge distance to increase peel resistance. Pinked edge tape is cut by passing the fabric between sharp discs pressed against a hard steel drum, and straight edge tape, a recent adaptation from non-aviation applications, is slit by heat melting with hot knives, which leave the melt residue on the edge to form a ridge. The reinforcing patches and tape ends are trimmed with 5 pitch per inch pinking shears to match the pitch of the pink tapes. A finishing tape of sufficient width to provide a minimum 3/8 inch contact on the fabric surface each side of the rib cap will be installed over all rib lacing. 2-inch width tape is normally used and intended as a weather protection for the lacing. Tapes over the wing ribs will extend a minimum 1 inch past the end of the rib lace reinforcing tape at the leading edge. Shaping the ends to a point or rounded off looks better than just chopping them off square. Continuing to the leading edge is optional. The most satisfactory method of installing finishing tapes and reducing the chances of pinholes through the tapes is to brush a wet coat of polybrush, reduced 3 parts to 1 part reducer, on a 3 to 4 foot strip on which the tape will be installed. As solvents in the fresh polybrush coat evaporate, the coating becomes more adhesive. The tape is applied over the wet polybrush and rubbed on with the brush or fingers to force it up through the fabric weave. The brush is used only as a tool to anchor the tape. It is not dipped back into the polybrush to apply a wet coat on the top surface while smoothing the tape, because a fresh coat will penetrate and dilute the first coat and allow the tape to release if it was installed with tension. Any small edges or sharp corners not conforming to the final contour or not bonding to the fabric surface should be ignored temporarily. As an aid to smoothing and removing any ridge of polybrush along tape edges, we recommend a small, wide-bottom container of polyfiber reducer be handy, in which to dip the brush tip and wipe any ridge from the surface before it dries. A narrow-bottom container will be easily upset. Any polybrush buildup along tape edges or brush drips on the fabric surface which dries unnoticed may be thermosoftened and smoothed later with the iron tip at 200 degrees before the poly spray is applied. A finishing tape over small protrusions such as rib lacing should preferably bridge and fair in the protrusion, not follow the exact contour. Solvent vapors trapped in the resulting cavity immediately surrounding the protrusion will not expand to cause a bubble because an escape route is provided by the rib lace. The same tape width used over the wing ribs should be installed over any false or nose rib ends, top and bottom, as an abrasion buffer. A minimum 2-inch wide polyfiber finishing tape is installed to reinforce all fabric seams. The tape is centered on the outside edge of cement seams and centered on machine-sewn and hand-sewn seams. Wider tapes are optional and recommended where a seam is adjacent to a sharp edge, needing a tape as a cushion against abrasion rather than using two overlapping narrow tapes. The minimum 2-inch wide tape should be installed as an abrasion buffer span-wise in the wing leading edges and stabilizer leading edges if a tape is not used over a seam in those locations. Wide tape or pieces of fabric trimmings are fitted over any openings not covered with the initial fabric fitting. Tapes should also be installed over the edges of all fabric-forming structures if not taped with a seam. Holes for control horns, strut fittings, hinges, and control cables will be reinforced with a fabric patch extending a minimum 1 inch from the edge of the hole. Installing a leather or plastic grommet around control cable or tube exit holes is optional. However, they would be coated during the finish buildup. Therefore, fabric patches should be installed first and any leather or plastic cosmetic trim added after the finish is completed. During the trimming and dressing with finishing tapes, wrinkles will develop where a hole is cut to fit around a small protrusion, and the iron may be used at 350 degrees to further heat-taut the fabric and remove wrinkles. Compound curves such as a wingtip bow and tail surfaces are dressed out using bias weave finishing tapes which easily conform to the contours. A 3-inch width will reduce to approximately 2 inches when pulling tight around a wingtip bow, and this gauge should be used when selecting the widths 2 or 3 or 4 inches for the various locations. Slitting and overlapping linear cut tapes to fit around compound surfaces does not look professional. The manual gives instructions for shrinking linear cut tapes to fit around compound contours when bias tape is not on hand. However, shrinking and forming linear tape is time-consuming. 1-inch wide tapes are usually used on all fuselage stringers. Particular attention should be given to horizontal finishing tapes on top of the fuselage aft of a skylight or aft of the windshield. There have been fatal accidents caused by fabric peeling from the top of the fuselage and losing elevator control after the fabric deteriorated or chafed through this critical area on high-wing cabin aircraft. Finishing tape is installed on plywood surfaces over a fabric butt joint and on the leading edge as an abrasion buffer. Installing tape around inspection access openings and over fabric overlap seam is optional. After the finishing tapes and reinforcing patches are completed, the next procedure will be to install the drain hole grommets with Polytack as detailed in Step 8. Drain holes are installed because atmospheric temperature changes cause the humidity in the air to condense on the inside of all aircraft surfaces and pool in low areas. Rainwater enters through openings in the sides and top, and when flying, everywhere throughout the structure. Taxiing on wet runways also splashes water up through any bottom holes. Therefore, provisions must be made to drain water from the lowest point in each fabric panel or plywood component throughout the airframe while in a normal stored attitude. A drain hole is installed on each side of a rib in flat panels that do not drain to one point, such as horizontal tail surfaces. Aluminum drain grommets are preferred over plastic because the plastic will melt when using the soldering iron to open a hole rather than serve as a guide to develop a neat round hole. Small round fabric patches over the grommets are optional. Drain holes through plywood skins are not reinforced. Seaplane grommets with a protruding lip are installed with the opening facing aft in all areas subject to splashing from the wheels, or in the case of seaplanes, used throughout instead of flat drain grommets. Before the seaplane grommet is installed with Polytack, a 1/4 inch hole is melted through the fabric. Pre-soaking plastic grommets or inspection rings in any reducer or MEK will cause the shape to distort and warp. After the components are completely dressed out with all the inspection hole rings, finishing tapes, reinforcing patches, and drain grommets installed, we will use the iron set at 225 degrees to remove wrinkles in patches and tapes and to lay down and bond any loose edges. Be careful about using the iron on concave surface wrinkles and cause the fabric to shrink and pull out. The next procedure is to apply the second coat of polybrush with a spray gun, listed as step number 9 in the manual. There's a wide selection of respirators available for protection from solvent vapors and spray mists during brushing and spraying operations. An organic vapor respirator covering the nose and mouth and filtering inlet air through activated charcoal filters may be adequate for brushing and light spraying operations. However, when working in heavy spray mist and when spraying polyurethane finishes, we recommend a hood respirator or a face mask with a fresh air supply from the compressor. The compressed air source then should be remote from the paint spraying area. Wilson Safety Products of Reading, Pennsylvania is one of the major suppliers of safety equipment in the United States. Safety equipment is available through companies listed under safety equipment in the telephone yellow pages in large cities. The second coat is applied with a spray gun with the poly brush reduced 3 parts to 1 part reducer. Any fabric area that does not show a slight gloss should receive a third coat. Particular attention should be given to finishing tapes and fabric over wing leading edges to assure adequate coating penetration to fill the fabric weave and avoid pinholes. Plywood surfaces are finished with the same procedure as the fabric panel areas after the fabric is bonded to the plywood. After the second coat of poly brush has dried about 15 minutes, close inspection should be made of all tape and reinforcing patch edges, and the iron used at 225 degrees to thermo-soften and bond any loose edges and remove any wrinkles in the tapes and patches previously overlooked. A much better looking finish and a considerable amount of sanding can be avoided by carefully running the iron, set at 225 degrees, on the edges of all tapes and patches to level and smooth the paint edges. Do not use a temperature higher than 225 degrees on finishing tapes and cause the width to shrink noticeably. Remove any coating residue from an aluminum iron sole plate by placing the cold iron on a polyfiber reducer-soaked clean rag for about 10 minutes. Then wipe the softened residue off with a rag. After all tape edges and reinforcing patches are checked and smoothed with the iron, the wing is ready for the first coat of poly spray detailed as step number 10 in the manual. Poly spray is applied only with a spray gun. Otherwise, rough brush marks will show through the finish. Poly spray is supplied in the correct viscosity and solvent balance for spray gun application. The first coat of poly spray readily reveals any coating flaws, drips, loose tapes, or pinholes. Poly brush can be applied any time during the coating buildup before the final pigmented finish to correct pinhole problems. The principle of a spray gun is to atomize the coating to a very fine mist and with proper velocity deposit it on a surface in sufficient quantity to flow together and form a continuous wet film. Too heavy a film will cause runs and sags, and large mist particles drying too fast will cause an orange peel appearance. All polyfiber coatings can be applied with any spray gun rated for lacquer and enamel, and it is important that the capacity of the compressor be at least equal to the rating of the spray gun being used. There are many good manuals published by spray gun manufacturers on the technique of adjusting and using paint spray equipment. Therefore, we won't spend a lot of time on spray guns other than stating that an air pressure of 35 to 45 pounds at the gun with the gun open is recommended when using suction-type spray guns. Adjusting the pressure with the gun trigger open compensates for the flow resistance in the air hose. This 3/8-inch hose is 50 feet long with many fittings, and the pressure drop between the pressure regulator and the spray gun is 25 pounds. The proper viscosity and other instructions are included on the product label and printed in the Polyfiber catalog. After the first coat of poly spray is applied, a Teflon or Silverstone coated iron may be used very lightly to smooth tape edges previously overlooked. However, heavy pressure will imprint the coating. If it is necessary to use the iron to lay down loose edges or remove a small wrinkle, place smooth aluminum foil over the poly spray surface. An alternate is to remove the poly spray with polyfiber reducer on a clean rag, do the rework, then rebuild the coatings. After a thorough inspection and all touch-ups are completed, the wing is ready for step number 11, the second coat of poly spray to build a sanding base. Poly brush is not a suitable sanding material. It is formulated to be an excellent fabric sealer and adhesive coating. Poly spray was formulated to block all UV radiation from reaching the fabric, as well as a sanding base to develop a smooth surface. Sanding should not be attempted until after the second coat because good sanding technique requires that the microscopic high points of a coating be removed and leveled with the bottoms of any pits. And when a coating is very thin, it is very likely tapes and fabric will be cut through over structural edges. After the second coat of poly spray has dried 30 minutes to 2 hours, depending on the weather, the surfaces are ready for step number 12, sanding. The surface may be wet sanded with number 280 grit 3M wet or dry sandpaper or equivalent. 9 by 11-inch sandpaper sheets are best used by folding across the center, then splitting in half. Fold in thirds around a rubber sanding pad which spreads the hand pressure more uniformly over the paper surface. Submerge the sandpaper in water to clean the paper surface about every 25 strokes, or squeeze water from a large sponge on the fabric surface to run across the sanding area. The sandpaper is refolded or turned over to use all 3 surfaces before discarding. A worn paper will have reduced slide resistance and can double the sanding time. Changing paper is more economical. Poly spray should be sanded only sufficiently to develop a smooth surface and not purposely sanded through to the poly brush. Do not sand over screw heads, rib lacing, or any other sharp edges which will quickly cut through the fabric. Free, inexperienced help when sanding fabric surfaces usually becomes very expensive when small patches are required to cover holes sanded through the tapes and fabric over rib laces and structure edges. After the sanding operation is completed, the sanding residue is washed from the surface, not allowed to dry because wiping the dry surface leaves a powder. Use only clean rags or a new sponge, not old laundry. After the sanding is completed, the component is then ready for step number 13. The third coat of poly spray. A minimum of 3 coats of poly spray is recommended, with no sanding on the last coat, because the coatings must block all ultraviolet radiation. The electromagnetic energy wavelengths we define as ultraviolet are not the harmless visible wavelengths we define as light. However, a fair gauge of ultraviolet blocking is to block all visible light. Special attention should be given to areas along ribs, stringers, and structure edges, where poly spray is usually sanded through. Coarse weave polyester styles usually require 4 or 5 coats to develop a suitable base for a smooth finish. However, the finer weave style, HS90X, is ready for the finish coat after the 3rd poly spray application. The completed coating system should fill the fabric weave. However, we strongly recommend that the coating buildup not completely hide the fabric weave or the tape edges, because excessively thick coatings may separate by tension when the fabric is pressed around the sharp edges of ribs, stringers, and fuselage structures. The polyfiber coatings are flexible and non-tauting, but must retain a certain amount of toughness to resist scratches and abrasions. There is a limit to stretching at any one point when pulled around the outside of a sharp radius. A common coating stretch and separation problem is caused by a misplaced foot along the edge of a catwalk. A thick, heavy coating buildup which hides all tape edges and fabric weave is a negative factor and only shows a lot of money was spent on unnecessary materials and many extra hours labor to add a lot of extra weight to the airplane. Very often, thick, heavy coatings hide very poor fabric workmanship. Good workmanship is indicated by straight finishing tapes and all tape and reinforcing patch edges laying down with no cutting or notching the tapes to conform to the surface, rib lacing alignment, uniform application of all coatings with no runs or orange peel, no sandpaper damage, clean sharp edges on trim lines and end numbers, and proper fabric tension throughout. Unfortunately, workmanship can't be packaged and shipped in a box or written into a manual. After the final coat of poly spray has dried about an hour, the wing is ready for step 14, the pigmented finish. In this case, we are going to use polytone rather than aerothane, an optional high-gloss, very durable, flexible polyurethane enamel. Polytone is a one-part, fast-drying finish formulated to be durable in hot, sunny climates and remain flexible in very cold climates. It is easy to repair and hide hanger rash and other damage. It may be rubbed with a compound and waxed to produce a gloss equal to any other one-part finish. Polytone is also recommended for metal components when the fabric is finished with polytone to assure a good color match. It is used on metal only over clean, scuff-sanded epoxy primer to assure a good bond. All pigmented coatings should be shaken in a double-action paint shaker for about 5 minutes. If the can has been sitting on the shelf for 4 or 5 years, allow about 15 minutes shaking. Then filter through a paint strainer cone. Before shooting the finish coat, wipe the surface lightly with a clean tack rag to remove any lint and dust particles. Never rub a tack rag hard on a surface because the wax will transfer to the surface. Spray a minimum of 2 wet, smooth coats of polytone, allowing approximately 30 minutes drying time between coats. An additional 3rd coat will depend on the polytone color. color of the surface being painted, spray equipment, and the technique of the painter. Dark shade finishes have better hiding power than light shades, and many times an inexperienced painter will waste half the paint into the air with an improperly adjusted gun and a slow trigger finger. When adequate spray painting facilities are not available, and it is necessary to control the drift from spray painting or control dust or insects settling on freshly painted surfaces, we recommend an economical paint spray booth be constructed using low-cost polyethylene plastic sheet on a light wood frame hanging from the ceiling. The Polyfiber manual gives suggestions for construction of a temporary paint booth with exhaust fans and inlet air filters. There are a long list of mistakes that can be made by any inexperienced painter when using any coating product, and the Polyfiber manual offers many suggestions to avoid mistakes during fabric covering and when painting fabric and metal aircraft. If a very smooth hand rub finish is the goal, Polytone may be lightly wet sanded with a 400 grit or finer sandpaper between coats after drying 2 hours or longer. Coarse sandpaper will cause sanding scratches which may telegraph through the final coat. After sanding, the surface should be washed with clean water and wiped dry with clean rags or paper towels to remove any sanding residue. Repeat the tack rag cleaning before the next coat. Polytone, like any pigmented finish, will bleed under the edge of poor quality crepe paper masking tape, resulting in botched trim lines requiring hours of rework. We recommend only high quality crepe paper and polypropylene masking tape, which, considering labor to rework, costs less than the bargain price tapes. The polypropylene masking tape is the most solvent resistant. One little trick to prevent trim line bleed showing is to first spray a light coat of the same base color along the edges. Then if there is any bleeding, it will be the same color. As a general guide, the drying time of air drying coatings is cut in half at each 10-degree increase in temperature and doubled at each 10-degree decrease in temperature. Polytone will dry dust-free in about 10 minutes in 70-degree weather. However, the film will be soft and may be marked with finger pressure up to 1 hour drying time. It is best to allow about 12 hours drying before using masking tape because taping over soft coats may imprint permanent tape marks. After installing trim lines, remove masking tape soon after the last coat of Polytone has dried print-free for a clean tape shear line. Don't use newspaper for masking because the ink will transfer to a fresh finish coat and require repainting. Light color should be applied first and overcoated with trim colors. Polyfiber finishes will not bleed when overcoated. Dark colors convert a large portion of electromagnetic radiation from the sun to thermal energy, which has been measured as high as 285 degrees Fahrenheit inside a black-painted wing at Phoenix, Arizona. Therefore, the recommended major color for fabric-covered aircraft or any aircraft is light shades with a minimum of complementary color trim because high temperatures accelerate the deterioration of fabric coatings and many components of an aircraft. When all water sanding is complete, a soldering iron is used to melt the drain holes through the fabric. After the Polytone finish has dried a day or two, it may be rubbed with a compound and waxed. However, the finish will still be soft because all the solvents will not escape from the film for 2 or 3 weeks. Therefore, it is best to allow time for the surface to become firm for easier compounding. Normally, the pigmented finish used on fabric does not add to the strength of the covering system and is not considered to be a part of the covering process approved under the original type certification or with a supplemental type certificate. However, the type of pigmented finish is a major factor that determines the service life of any fabric-covered system. The polyfiber covering on some of these aircraft were installed in the early 1970s and are still looking good. Any type of coating which will not flex and stretch the same as the polyfiber subcoats and allow the fabric to carry all the air loads at all temperatures, especially after aging in the sun and hot climates, will crack. Therefore, we strongly warn against using brittle automotive enamels relabeled and sold as aircraft metal finishes, and pigmented butyrate dope is a finish over polyfiber covering materials.
As a wrap-up, I want to discuss the durability of covering materials and finishes in general.
There are hundreds of aircraft owners and former owners who will agree that the combination of polyester fabric and modified or unmodified cellulose dope coatings and automotive finishes do not give years of trouble-free service. Cracks and peeling from the fabric are the major complaints. We talked with Bill Biles, an aircraft refinisher in Southern California. Bill only recommends the Stitz polyfiber process and provides a 1-year warranty. If requested to cover with any other method or system, no warranty is provided. Polyester is best used on aircraft when it is allowed to absorb all the flight loads with flexible, good bonding coatings used only for protection. This 6-month-old wing covering is off an aircraft that was recovered and put back into service using the Polyfiber STC number. And according to the records and logbook, only polyfiber materials were used. However, this fabric is coated exclusively with an FAA-approved polyurethane primer and finish, and its characteristics is typical of all brands of fast-drying, high-gloss, acrylic-based polyurethane coatings competing for the automotive repainting market. The finish in subcoat is brittle at room temperatures and becomes even more brittle as the temperature drops. When the coatings are flexed, they snap like glass and peel off with less resistance than nitrate dope, leaving the fabric bare. We've seen the flammability of the other coatings and will now check the flammability of this acrylic-based polyurethane on polyester fabric, which is advertised as being non-burning. It ignites at a higher temperature than cellulose coatings. However, once started, it burns longer and just as hot. The discouraging experience of an expensive covering job gone sour has caused many former aircraft owners to take up other types of recreation. A close inspection of fabric-covered aircraft tied down at small airports and questions to the owners can be very educational and possibly prevent making expensive mistakes. With a little experience in reference to the manual, it is easy to recognize the different types of covering materials rather than depending on the logbooks to be accurate. False and incomplete information in the aircraft records is quite common when describing the covering materials used. All polyfiber fabric is identified with a stamp at 3-foot intervals. Remember, the first coat Polybrush has a red oxide tint and is also available untinted. Polyspray is an aluminum pigmented coating. When a fabric sample is available, a burn test also sets the polyfiber coatings apart from cellulose and acrylic-based polyurethane coatings. Firm thumb pressure on a fabric panel which leaves a temporary depression is an easy test that distinguishes the polyfiber coatings from all other types of solvent-borne coatings. If it ringworms or peels off, it isn't polyfiber coatings. As for the durability of finishes, there's no finish that will match the unlimited service life of properly protected polyester fabric. Even the best brands of the most durable type of metal finishes on metal aircraft stored outside in the southwestern sun in adverse weather start to lose their gloss in about 8 years. The high-gloss, fast-drying, brittle acrylic-based polyurethanes developed for the automotive repainting market and widely used to paint metal aircraft and unfortunately many fabric aircraft start to deteriorate and become dull in about 3 years when exposed to the sun and weather. It is common knowledge in the paint industry that epoxy finishes are about as durable as synthetic enamel. After about 2 years exposure, they start to chalk. Years of observation, experiments, and weathering tests with all types of fabric and coatings by Ray Stitz indicate the best compromise if the aircraft will be stored in a hangar, not exposed to severe environmental pollution, is aircraft quality polyester fabric protected by a thin, light, non-tauting, non-flammable, good bonding, flexible coating system, which is easy to repair and can be rejuvenated and refinished when the need occurs, and a gloss maintained with a good wax polish. The Polyfiber covering system with polytone finish meets that specification. It is our recommendation that aircraft stored outside in the sun and exposed to acid rain, fog, dew, and other pollution be finished with a flexible, durable polyurethane enamel especially formulated for fabric on aircraft, such as our aerothane enamel. About any type of fabric covering material and finish will appear to be satisfactory when the aircraft is only displayed in a museum or stored in a locked hangar and very seldom flown and always roped off from curious fingers when on display. However, the true test of a total covering system is many hours of flying and years of trouble-free service.
And my final words of advice, if you want to do it right the first time, don't substitute materials and follow the manual.